So welcome to third tutorial of this course. So in this tutorial, we'll be learning how to identify point group, and we will take different examples, different solved examples. We will take 2D objects, we'll take 3D objects. We'll also take different molecules. So let us start this tutorial. So identifying point group is very, very important for this course. So you must need to learn very, very carefully that how to identify point group of a molecule, because rest of the course totally depends on this particular step. Okay, so let's get this going. Tutorial 3, and today we'll be discussing point group identification. So basically what we need to do is we need to identify what are the symmetry elements present and what are the corresponding operations, right? Given a range of different things, and what happens if we distort a molecule, how does the point group changes, and so on and so forth. Okay, all right. So let's say if you have, we will start with 2D objects, random objects we will choose. So let's say if you have a smiley face, it's a circle with two eyes and a smiley, right? So what do you think the point group of this will be? So if we try to list down the elements, we have E, and we have a C2 which is passing through the center, right? Like this. So you have I'm not going to draw for all the molecules, I'm just mentioning it for the sake of this first molecule now. So sigma V1, and we will have sigma V2, right? So sigma V1 will be the plane which is perpendicular to the plane of the board and carrying C2, and sigma V2 will be the plane which is in the plane of the board and also carrying C2, right? So this is the case like water molecule. So you have C2V point group, right? Okay, so that was easy. So now let's look at another drawing like this. So what we have today is a arrowhead, something like this. Okay, not the complete arrow, just the arrowhead. So here we had smiley, now we have arrowhead. So arrowhead also has the same set of symmetry elements, if you notice. So you have a C2 running through like this, and then you have sigma which is in the plane of the board, sigma which is perpendicular to the plane of the board, both carrying C2s. So again the point group will be C2V, right? So that is easy again. Now let's look at hash sign. So that can get a little tricky. What is the point group here? So hash sign. Consider that these lines are parallel and slightly angled to this one. So the vertical lines are not completely vertical at a certain angle. Let's say the angle between this is 80 degree or something, right? Okay. So now what will be the point group? So if you notice that you have a C2 which is perpendicular to the plane of the board passing through the center. Then you have another C2 which is bisecting these two like this. Let me just draw it. So you have one C2 like this, another C2 like this, another C2 like this, right? So you have three C2s, and all three of them are perpendicular to each other. So you have E, C2, C2 prime, C2 double prime, or you can also say two C2s which are perpendicular to one of the C2. So you have C2 prime, C2 double prime. What else do you have? Do you have I here? Yes, we have I. What else do you have? You have three sigmas. Each of the C2 will be containing one sigma. So you have sigma 1, sigma 2. None of these will be sigma h. So I'm just writing sigma. You can say sigma V1, V2, V3, and so on, or D1, D2, D3. Right? So now this goes into what kind of point group? Any ideas? So let us leave this to you as a home assignment. So home assignment. Now we have listed this elements. Your job is to find what will be the point group. Okay. Now let's take another example. So what we have is a snowflake. Okay. So snowflake is, it looks something like this. Now if you carefully see that it will have a C6 axis. It's almost like a benzene case, right? So it has a order 6 symmetry. So it will have C6 axis, which is perpendicular to this, I, sigma, H, and so on and so forth, right? So what will be the point group? So you have E, C6, C3, C2. Then there will be C2s which are running in the plane of the boards, and you have sigma H, and you will also have sigma Ds, and so on and so forth, right? You will also have I. So again, what will be the point group here? So I will ask you to do that. Okay, so try to work it out. So similar to this, the way I have picked up few shapes, try to look around where you're living or where you're studying, take different objects and try to find out what point group does it belong to. So that will give you some practice of how to identify point group of a object or a molecule. Once you know how to find out point group of an object, the molecule will also be an easy case. Okay, so these were 2D objects. So let us look at some 3D objects. So the first example I have here is styrofoam. I typically, if it's an offline class, I typically carry these items so that it is visible to all of you. But in online class, I can only draw, but you should be able to imagine how a styrofoam cup looks like. So basically you have it's not a right circular cylinder, it's something like this, right? So you have a styrofoam cup, which is used to drink tea, right? A portable cup. Now, what will be the point group of this? So if you think that if you bisect, or if axis which is going through the center of this will be what kind of axis this will be? This will be C infinity axis, right? And if you now take the planes which are bisecting in the middle and containing this axis, so there will be infinity such planes, which will be, all of them will be sigma V's, and then of course you have E, right? So this basically is like an HCl molecule. So you have C infinity V point group, right? So that is easy. Now let's say if we add handle to this, okay? So now ceramic mug, which you use to drink coffee, let's say, mug with handle. So how does it look? So you have, now this is like, let's say you have a right circular cylinder kind of thing, and you have a handle, right? So, and from the top, if you look, it looks something like this, right? So this is a view from the top, this is from the side. Okay, so now what will be the point group here? So let us list down the elements. So you have E, what else do you have? Do you have any C2 here? Any rotational axis? You don't have any rotational axis because of this handle destroying the symmetry. So all you have is one plane which is passing through this. So vertical plane which is passing through this, right? So you have sigma. So the point group will be CS. There is no other symmetry element or operation, right? So that is easy. Likewise, you can pick up any object around you and try to work out different things. Now let's say if you have a propeller, you must have seen propeller like, for example, exhaust fan in your home, right? So propeller with 3 blades. How does it look? So you have a circle, which is the center of the motor, and then you have a blade kind of thing where some part of the blade is coming out of the plane. So let's draw that thick, right? And this part, let's say, is going behind the plane of the board. Likewise, that's how it will propel. All the blades will not be in the plane of the board, right? So there'll be a little twist to the blades. That's how it will propel. Okay. So now what will be the point group? What all symmetry elements it will it will contain. So you have E, then you will have C3 passing through the center and perpendicular to the plane of the board, and you will also have 3 C2s. Now the C2s will be bisecting each blade like this, okay, in the plane of the board. So half of the blade is coming out of the plane of the board, half of the plane is going below the plane of the board, and when you do this rotation, this half goes there and this half comes here, and similarly this thing also is reflected, right? So this is how it will have 3 C2. So that means there is no other plane or anything, any other symmetry element. So this will be a D3 point group. Similarly, you can have propeller with 4 blades, so then it will be D4 point group, and so on and so forth, right? So propeller with 3 blades. So now this is for 2D and 3D objects. Let us now look at some molecules also, and let's see what happens if we distort these molecules. So we'll be looking at molecules with, because regular geometry we all understand by now, right? But what happens if we distort these molecules, how the point group changes? With distorted geometries. So when I say distorted geometries, we will just change the bond length of one particular bond hypothetically, okay? I mean, it can happen in real time also, depending on what kind of ligands are available and so on and so forth. So here we'll be doing only hypothetically. So you have MX3 molecule. Let's say it is, the first molecule is trigonal planar. So trigonal planar is you have M, X, 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 right? So this one is simple D3H. Okay. So I'm not going to work out this molecule. I'll just tell you how the distortion changes the point group now. So let's say the distortion is, so this is my distortion, where what I'm doing is I'm lifting M out of the plane. So what happens if I lift M out of the plane of the board? So then basically it becomes like an umbrella. So you have X, 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 right? So top view still looks like this, but what you have done is you have lifted M out of the plane of the board. So now from D3H, now you have gone to C3V, right? Later on, we will see how these kind of distortions are actually very, very important to understand. But today we are just focusing on how a particular distortion changes the point group, okay? So you have from D3H, you went to C3V because what you have done is you have basically killed sigma H in the process, right? So I can say if I'm removing sigma H out of this, so I will lead to C3V kind of thing, okay? Rest of the planes and all other symmetry elements are still present, and it must follow the closure property of the group, which it does follow, right? So what you are left with is C3V. So let us do similar kind of distortions in different molecules and see. So let's say if you now have MX4, which is originally tetrahedral. So then you know how to draw a tetrahedral molecule. So you have X, 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 right? And this is a TD point group, tetrahedral. Now what is the distortion here? Distortion is, so what question says, slightly flattening the molecule along one of the C2 axis. So what you are doing is where is the C2 axis? Let us draw the C2 axis here. So this is my C2 axis in the plane of the board. Okay, this will be reflecting these two axes and these two axes, right? So now if I flatten this molecule along one of the C2 axes, how does it look? So these two will not be flattened because I'm trying to flatten about this C2 axis. So these two will not be affected. Or let's say these two will also be affected. Let's do one by one. So let's first distort only these two angles. Okay. So what I have is basically you have M, X, X, and what you have is XX. So now this angle is no more 109 degree 28 minutes. This angle is still the same as tetrahedral angle. So that would mean what will be my point group? So now my point group will be C2V. And how do I get C2V? Try to work it out yourself. Here I'm giving you the point group answer and I'm asking you to find out all the elements and see if this is correct or not, right? Similarly, if you compress this angle also, again you will end up getting C2V point group, right? So try to work it out and see this kind of distortion, how this kind of distortion, what all elements, what all symmetry elements are killed in the process when you do this distortion. So if you have difficulty in understanding this distortion, maybe what we can do is we can draw this molecule inside a cube and do the same distortion. Okay. So inside the cube, if you draw, it will be a tetrahedral. You have center, one bond going to this diagonal, one bond going to this, vertex, this vertex, and that vertex, right? So this gives you a tetrahedral. So this is a TD geometry. Now the distortion actually takes it to a different one. So let's see what is the distortion here. What we have done here is this is my center again. So these two bonds are not compressed. Let's say what we have done is we have compressed only these two bonds. So instead of going to vertex, now they are falling on one of the face diagonals, right? This is how the distortion looks like. So instead of all the way to the vertices, now I'm resting my bonds or my atoms at the somewhere in between the face diagonal. Okay, so now that means this angle, which was initially 109.28 minutes, degree 28 minutes, now this is less than 109 degree 28 minutes, right? Rest of the angle is, or the other angle is still the same. It will of course affect the other angles also. So now what all elements are killed in this process, that you have to visualize. So what you have to do is you have to sit inside the cube yourself and see how the bonds are changing or how the elements are affected. How many C4s or C3s or C2s are there initially when it was a tetrahedral, and now what we are left with is only C2V. Is that correct? Do we have more symmetry elements? Do we have less symmetry elements? So try to work it out. So I have given you an approach how to solve this problem, this kind of problems, but try to work it out yourself. Otherwise, we can always discuss during the interaction session. Okay. All right. So let's take more examples like this. So this one is simple. So you have MX4. Originally, the geometry is square planar. So that would mean a D4H point group, right? So you have M, X. It's like PTCL4. So you have D4H. Again, we are not going to discuss. And now the distortion is elongating two trans MX bonds. So that means I have to elongate these two, and these two are kept at same distance. So that would mean my molecule now looks like. So I have done this distortion. Now how this thing will change. Now what do I left with? So I am left with, so first of all I have killed my C4, right? Now there is no central C4 axis. Principal axis is now reduced to C2, which is coming out of the plane of the board perpendicular to this, so that these two are reflected and these two are reflected, right? That is C2. And then you will also have C2s, which will be, so these C2s are also killed. Now you don't have this C2, right? This C2 is not there. So what you have is this C2 and this C2. So basically now you have two C2s perpendicular to your original C2. That means it's a D2 point group. Other than that, you also have, you're still left with sigma H, you're still left with I, right? So sigma H, and then you will have one sigma here, so sigma 1, sigma 2. So basically 3 sigmas are there, right? So this will be D2H kind of point group. So let us verify this. Let me look at D2H character table. Yeah, so D2H should have E, 3 C2s which are perpendicular to each other. So you have this I, and then 3 sigmas. Again, if one is along XY, the other will be YZ, third will be ZX. So which we have, right? So that is correct. So basically by elongating these two bonds from D4H, we are going to lower symmetry point group. We are going to D2H, right? So why did I say lower symmetry point group? Because here the order of the group is lower, right? Okay. So now let's look at more examples. So you have MX5, which is trigonal bipyramidal. What will be the point group here? So let me draw the molecule. So in this case, equatorial bonds are of different length and axial bonds are of different length, right? So this is a trigonal bipyramidal case. What will be the point group? Point group is D3H here. And the distortion I'm looking for is elongating two axial bonds. So if I'm elongating two axial bonds, they are anyways elongated, right? So if I elongate it further or decrease the length of these MX bonds, it should not change anything. So the point group remains as D3H. Okay, so this is a simple case. Now let's look at more such trigonal bipyramidal cases. So you have MX5 trigonal bipyramidal, and the distortion now will be different. So again, this is D3H, and the distortion is, what we are doing is elongating one of the equatorial bonds. So if we elongate one of the equatorial bonds, what do we get? And what are the symmetry elements that we are killing? So let's say this is elongated. Now try to think that where are we now? So this looks like a water molecule. So what you have got is EC2. C2 is passing through this MX bond. Sigma is again the plane of the, one will be the plane of the board, another is perpendicular to the plane of the board, both containing this elongated equatorial bond MX. So you have sigma V1 and sigma V2, right? So point group will be C2V. So again, from D3H, we have gone down to C2V, gone down in order of the group. Okay. Okay, let's look at more examples. I have two more examples. So we have, again we have MX5, and we are starting geometry is trigonal bipyramidal. So and the distortion, so this is D3H. Distortion here is, while we are elongating one of the equatorial bonds, one equatorial bond, and simultaneously we are shortening one axial bond. Okay, so let us see how it works out. So you have mx elongated, these two are not changed, this one is reduced in length, this one is still the same. Now what do you think will be the point group? So what do you have? So now if we try to put a C2 axis here along this mx bond, I do not have any C2 axis, right? Because although these two will be exchanged, but these two x's will not be exchanged because their bond lengths are different. What about sigma? There is no sigma in the plane of the board, but there is one sigma which will contain the two axial and one equatorial and this m atom, right? So these two will be reflected. So we have E and we have sigma. Any other symmetry element? We don't have any other symmetry element. No C3 axis here because these three will not be rotated. So the point group now is CS point group, E and sigma, that is all, right? So that is also easy. But see, now when we are doing any kind of distortion, what you have to keep in mind is that what are the symmetry elements originally present, and by doing this process, out of those symmetry elements, what elements got killed because of distortion. Okay, so if you can think in those lines, you should be able to find an answer very quickly. Let's do one more example and then we can stop. So let's say MX6 octahedral case. So let's say, let me do one example and one I will give for home assignment. Okay, so elongating two trans bonds. This is a simple one. Okay, let's do both. So how does it look? So you have M, all the bonds are of same length, right? So they are equally spaced out. Okay, now this is OH point group. Now this is the distortion, elongating two trans bonds, which can be anything. Maybe you can take top and bottom, or you can take this one, anything will give you the same result. So let's say elongate these two bonds. So what happens? Now what we have done is we have killed a lot of elements. From OH we have gone down to D4H. Now how does it work? So try to again find out missing elements, what all elements are killed in the process, and hence this becomes a case like PTCl4. Okay, so D4H, you all know by now that what all molecules would look like D4H. So this looks like a PTCl4 kind of molecule, right? Okay, let's do one last example. This is a slightly tricky one, so I want to cover this title again. Okay, now here let me first write the distortion. So it says close 90-degree angles between three MX bonds in both sets of cis related positions. So it is little tricky to understand what the question is asking. Cis related positions. So if we try to draw a coordinate system and put the molecule onto this, so you have basically M sitting here, x going along the coordinates, which is x, y, z, right? And the other three are sitting like this, right? So now if you consider this x, let me circle this, this x, and this x, they are one set of cis related positions. The other three are other. So let me draw it with a different color. So the pink set is second set, right? Now if you notice that the angle between x-axis, y-axis and z-axis is 90 90 90, right? So now they are saying that close that angle. So it's like an umbrella which is opening up, and then you're closing down x, y and z axis to an angle less than 90 degrees. So x, y, z are no longer perpendicular to each other. They form like a cone, right? So if I'm looking from the top, it looks something like this, something like a star. That's how octahedral in general would look like. But now these three vertices are not meeting at a point where those axes are forming 90-degree angle. So if I look from the side, it looks something like this. It looks like a cone shaped thing. So this is the top of the star, and these are the bonds, and this is the third bond is at the back, and the other one will be, so you have one bond in the front. So this is how it looks from the side. So this is the top view and this is the side view, right? So I hope it is easy to see now that what all elements got killed. So I have already drawn this molecule for you, so I would give you as a home assignment. So try to work it out. Try to work it out. What is the point group of this molecule? So try to see, this is the most complicated one, but if you can't find it, we'll again discuss during interaction session. But if you can find it, well and good. So try to work out what all symmetry elements are killed in the process and what is the point group of the final. So I think that is all. So we have discussed a lot of examples today. So keep practicing. So this course requires a lot of practice. So if you can't figure out the point group of a molecule, the rest of the course will be very, very difficult. So I would suggest you to practice a lot of molecules, and then we can cover the rest of the topics very easily. Okay. So that is all for today. Thank you.